All right, welcome, ladies and gentlemen. This is Ralston Valley High School's AP Chemistry Lecture Series, Chapter 10, Lecture number 3. Today we're going to be talking about vapor pressure. So let's go ahead and get started. All right, so the main topic of conversation in this lecture is an idea we've hit on before, but we're going to get into greater detail here today, which is the idea of vapor pressure. Definitions first here, we define vapor as being the gas phase of a substance that normally exists as either a solid or a liquid at room temperature of around 25 degrees Celsius and 1 atmosphere of pressure. So think about it for a moment here. We've already talked about, like, say, gas phase water vapor, which forms as a result of evaporation off the surface of a liquid. Now, even though the boiling point of water is 100 degrees Celsius, we still see water evaporate at temperatures well below that particular boiling point temperature there, because, again, we would expect to see, due to the random thermal motion within the liquid phase species, some of the molecules of water will have enough energy to escape out of the liquid phase and into the gas phase, even below the boiling point. So it's not just evaporation that can produce gas phase vapor, but also sublimation as well. Even in solid phase, species will have some tendency to, just due to random thermal motion, gain a little bit of kinetic energy in terms of a collision between particles in the solid phase, and allowing them to escape out of the solid phase into the vapor phase. So again, we expect to see an equilibrium established between liquid and gas phase species within a closed system, or between solid and gas phase species. So let's go ahead and take a real quick look here at a diagram. We've drawn a manometer here for you on this particular page. And let's imagine that within that manometer, we've got a little bit of liquid phase water, H2O. And we've got a column of mercury that is going to be separating the bulb side of our manometer from the tube side over there. And note again here, this is a closed tube manometer. Now, the liquid phase water molecules are attracted to one another due to the presence of hydrogen bonding. That's primarily the attractive force that exists between those water molecules. The water molecules hold together into the liquid phase, but again, there is thermal motion within the liquid phase, and we expect then, from time to time, just due to a random collision that happens into the surface of the liquid, one of those water molecules might pick up a little bit of enough energy to be able to escape, to overcome that attractive force that holds it into the liquid phase, to overcome those hydrogen bonds. And in doing so, that's going to escape from the liquid phase into the vapor phase, and we'll see now the production of some vapor phase particles. Now, at the same time, those vapor phase particles also might, just due to random motion, strike the surface of the liquid, be attracted to the water molecules due to, again, the hydrogen bonding that's present there, and as a result, they could then return back into the liquid phase. And at a certain point, when we get enough of the vapor phase particles present in the gas phase, we would expect to see a point of equilibrium. That is, where the rate of evaporation off the surface of the liquid is exactly balanced by the rate of condensation from the vapor phase back into the liquid phase. And the pressure that those gas phase molecules exert at a particular temperature when the system is in equilibrium is what we refer to as the vapor pressure of that system. And that would again push up our column of mercury, which could be measured within a manometer. So again, we see, due to evaporation within the liquid phase, we expect to see equilibrium established within a closed system, and the pressure exerted at that equilibrium is the vapor pressure. And we'll move on to the next slide here to see what factors influence that vapor pressure. So now that we have seen that even below the boiling point of a liquid, we would expect to see some vapor phase particles present within a closed and isolated system, let's talk a little bit now about the factors that affect the vapor pressure of a particular species. Again, recognizing that what holds the liquid together in the liquid phase, rather than allowing all of the particles to move into the vapor phase, are the intermolecular forces of attraction, which again for water were primarily those hydrogen bonds, but in other species might be London dispersion forces or dipole-dipole interactions. Logically thinking then would tell me that the stronger those intermolecular forces are, the less likely particles are to escape out of the liquid phase into the vapor phase. And therefore, we'd expect to see lower vapor pressures from species that have stronger intermolecular forces. And conversely, if we have very, very weak intermolecular forces between particles, those particles would then require very little energy to escape the attractive forces that hold them in the liquid phase. And therefore, more of those particles will escape at a given temperature, meaning that substances that generally have weaker intermolecular forces generally tend to have higher vapor pressures at a particular temperature. Now, with that general idea in mind, let's look at the second factor that influences vapor pressure here, which is going to be temperature. And this one should make logical sense. If I take a liquid and I heat it up, I'm adding more random thermal energy to the system, meaning more of those particles within the liquid phase are likely to have high enough energy to escape out of the liquid phase into the vapor phase. So in general, as we increase the temperature of a liquid, we increase the vapor pressure of that liquid due to the increasing rate of evaporation at higher temperatures. And that again kind of explains ideas you've seen before, which is if you want to dry your clothes, you put them in the dryer and you turn up the heat. You don't put them in the dryer and make it colder in there. So we see increases in rate of vapor formation at higher temperatures. Now, that being said, a related topic here that we're going to be kind of talking about in terms of its relationship to vapor pressure is an idea here called the heat of vaporization. By definition, the heat of vaporization is the energy required to vaporize 1 mole of liquid phase species at a pressure of 1 atmosphere. And recognize again that this is a unit of energy here, we report this heat of vaporization in units of kilojoules per mole. Now, heat of vaporization, given the conversation we just had, is essentially related to that idea about the strength of intermolecular forces within the liquid phase species. If the particles are more strongly attracted to each other, that is, if there are stronger intermolecular forces, we'd expect it to require more energy to move those particles from liquid phase into the gas phase because we have to separate those particles, overcoming those intermolecular forces of attraction to move it into that gas phase. And therefore, species that have a stronger set of IMFs present generally have higher heats of vaporization. Now, let's take a look here at a real quick graph with those definitions and kind of general ideas in mind here. In this particular graph, what we're looking at here is the effect of the temperature on the distribution of molecular energy within a sample. And in this graph, along the x-axis, we've got particular kinetic energy. And then on the y-axis, we have a number of molecules with that given kinetic energy. And the key thing to note here is the idea that within a substance at a particular temperature, not all of the particles have the same kinetic energy. Some of them are moving faster, some of them are moving slower. I think a really good analogy would be to thinking about if you put like a room of kindergarten students together and you just let them run wild and free, they're bumping into each other, crashing all over the place. Some of them are going to be moving fast at a given point in time. Some of them will be moving slow. You could imagine even from some collisions taking place that every once in a while, one of those particular collisions might result in 2 particles moving very, very, very fast at high speeds, and another collision might essentially bring things more or less to a standstill. So again, there's going to be a distribution of different kinetic energies within the system that those particles have. Now, in general, remember from our discussions earlier in the year, temperature is directly proportional to the average kinetic energy of those particles, which means as the temperature increases, we'd expect to see more of the molecules moving at a higher speed. So if we draw here a little distribution curve here, some of the molecules will be moving very, very slowly. Some of them will be moving with greater velocities. And I could look at the peak of where that curve lies there as a measurement more or less of the average speed of those particular particles. Some moving faster, some moving slower. If I increase the temperature of the system, there are not going to be any more molecules than there were before, but the distribution of how many of those molecules have what particular amount of kinetic energy is going to change. At higher temperatures, more of the molecules are going to have more kinetic energy, and fewer of the molecules are going to have lower kinetic energies. And as such, the net effect of that is to shift that curve at higher temperatures to the right. That is, more molecules would have a higher kinetic energy, and we see the peak of that curve shifts moving rightwards at higher temperatures. Now here's the big key idea they want you to get out of that graph. Remember, to escape out of the liquid phase into the gas phase, molecules have to have enough kinetic energy to overcome the intermolecular forces of attraction that hold them together into that condensed liquid phase of matter. And if I just draw a little line along my graph here showing the amount of energy required to escape from the liquid phase, you see that at higher temperatures, a higher portion of those molecules have enough kinetic energy to escape, and therefore we would expect to see then more of those particles entering into the gas phase, generating then a higher vapor pressure at higher temperatures. So long story short, smaller intermolecular forces, weaker intermolecular forces mean higher vapor pressures, and higher temperatures mean higher vapor pressures. Let's move on to our next slide. All right, so on this particular slide here, we're going to look at how to predict vapor pressures quantitatively. Now, before we get into this discussion here, recognize here for me that the AP test in recent years has not asked you to make quantitative measurements of vapor pressure using this equation. But that being said, it's really useful to understand the math behind how this works because they have been asking very frequently qualitative questions about vapor pressure for you to answer, in particular on free response questions. So what I want to look at here is the idea that vapor pressure increases, but non-linearly with an increase in temperature. Thinking again back to that distribution of molecular energies on the last slide there, that graph we just looked at there. Remember, as we increase in temperature, we shift that curve to the right, which pushes more of those molecules past that threshold line of energy required to move into the gas phase. And at a certain increase in temperature, we expect to see a large increase in the number of particles with enough energy, again, because really what we're looking at there is the area under the curve of the number of particles with that amount of energy in this particular distribution of molecular energies graph. So that being said, we see generally a nonlinear increase in vapor pressure as temperature goes up. Now, that being said, nonlinear systems are harder to deal with, so one thing that can be very useful for us is to linearize our data, looking for the relationship then that exists between vapor pressure and temperature. And as it turns out, through experimentation, we find an equation here, which is a big, huge mess here. That is, the natural log of the vapor pressure is equal to minus the heat of vaporization divided by the gas constant R times the inverse of temperature plus a constant C. And what I really want you to look at here is not just the actual equation itself overall, which is a kind of big, messy equation, but fundamentally I want you to see that this particular equation describes a straight line. That is, it is in y equals mx plus b format, where the y variable, the dependent variable here, is the natural log of the vapor pressure. The x variable is the inverse of the Kelvin temperature, and the slope of that line is minus heat of vaporization divided by the gas constant R. So, long story short here is what that really tells me is that the natural log of the vapor pressure varies linearly with the inverse of the Kelvin temperature. And you see here the two graphs I've given you. The first one shows the vapor pressure versus temperature, which you see increases non-linearly. But then on the right-hand side there, you see if you graph that natural log of vapor pressure versus 1 over the Kelvin temperature, that is the inverse Kelvin temperature, you see we get a straight line graph. And the reason why that in particular is a very, very useful tool is I can very easily measure the slope of that straight line graph. And if I measure the slope of that straight line graph, recognizing from my equation over here that that slope is equal to minus heat of vaporization divided by the gas constant R, the gas constant is a constant, which means I can find the slope of that line and use it to determine the heat of vaporization of a particular liquid phase species. Once I know that heat of vaporization, then I could go about essentially manipulating this equation here to solve for whatever variable is missing. So if I know the heat of vaporization, and I also know the temperature T at which this is occurring, I can essentially just solve then for the vapor pressure within this equation. So that would then allow me to determine at any given temperature what the expected vapor pressure of a liquid actually is. So long story short, this is the math of exactly what we were talking about in the previous slide. That is to say, if the heat of vaporization is larger, that means it takes more energy to move those particles from the liquid phase into the gas phase. We'd expect then to find the vapor pressure to be smaller. Or alternatively, from this equation, as the temperature goes up at higher temperatures, we would expect to see the vapor pressure go up as well. So again, my equation really justifies for me here the understanding that temperature increases lead to increases in vapor pressure, because if you have a look at that slope of that line, the slope is not the heat of vaporization over the gas constant R, it is minus the heat of vaporization over the gas constant R, which implies if temperature increases, the value of 1 over T becomes a smaller number, and therefore that entire right-hand side of the equation becomes less negative, meaning the natural log of that vapor pressure is going to yield then a larger number, and then the vapor pressure itself, therefore, is getting bigger. So increases in temperature make vapor pressure go up. And furthermore, heat of vaporization essentially is a mathematical tool I can use to really kind of see mathematically how hard it is to overcome those intermolecular forces, moving things from liquid phase to gas phase. And we can justify that mathematically by understanding that if heat of vaporization is a larger value, that means that that right side of the equation is a more negative value, meaning that natural log of that vapor pressure giving a more negative value would mean the vapor pressure must therefore be smaller. So with a higher heat of vaporization, we'd expect then to see a lower vapor pressure at a given temperature. So this equation is essentially the math behind the qualitative understanding we came to on our last slide. So for those of you who are kind of mathier people, you might want to use this equation in terms of your justifications, but for people who like to think qualitatively about our systems, by all means, you're welcome to just justify your reasoning on most AP questions qualitatively rather than quantitatively that we've seen in recent years on the AP test. All right, so now that we've had a look at vapor pressure, and in particular, we've had a look at the equilibria that exists between phases resulting in vapor pressure, it's time to take a moment to revisit an idea which we taught you at the very start of last year about phase changes. So again, we're going to briefly explore here the phase changes that are possible, and we'll get into phase diagrams, which we introduced you last year as well. So to begin with, let's think about the possible phase changes that could exist between the standard phases of matter, that is solid, liquid, and gas phase. If you begin in the solid phase and you end up in the liquid phase, like say you take a block of ice and turn it into liquid phase water, you would say that that substance has melted. So melting is the phase change that occurs between solid and liquid phase. And in order to melt a substance, you have to add energy to the system, which would imply that process, therefore, of melting is an endothermic process. And if you then took that liquid phase water and heated it further, again, making this again an endothermic process, you could change that liquid substance into a gas phase substance. That process we refer to as evaporation. And if we're adding energy by increasing the temperature there, what we're really talking about then is boiling as a phase change there. And then conversely, if I took the gas phase substance and cooled it down, think about, let's say, gas phase water vapor particles touching a cold mirror in your bathroom in the morning when you're taking a shower. You would see little droplets of liquid phase water form on the surface of the mirror, and we call those droplets condensation. So the process of condensing involves a phase change from the gas phase into the liquid phase. And then again, another familiar one, if we further cool those liquid droplets down below the point of 0 degrees Celsius at standard pressure, we would expect to see those liquid phase droplets freeze, and therefore freezing is the phase change that occurs between liquid phase and solid phase. Now, recognizing that to make something melt, we had to add energy to the system, that implies that to make something freeze, the opposite of melting, would mean that we're removing energy from the system, and implying, therefore, energy is being released into the surroundings. Therefore, freezing is an exothermic process. And the same logic would apply to the process of condensation. To condense a gas means that the gas is going from a higher energy state to a lower energy state, from gas to liquid, and therefore must be getting rid of energy to the surroundings, meaning that is also therefore an exothermic process. So those are the four most familiar phase changes. There are two more, however, that we introduced to you last year. If you begin with a species in the solid phase and it transitions directly to the gas phase without passing through a liquid phase in between, we refer to that process as sublimation. Really familiar substance that undergoes sublimation is dry ice. Again, dry ice is just solid phase carbon dioxide. And we call it dry because at standard pressure of 1 atmosphere, it doesn't melt. It doesn't leave a puddle of liquid phase carbon dioxide as it heats up. Instead, it sublimes directly into the gas phase. So going from the lower energy state in the solid phase up to the higher energy gas phase means it has to absorb energy from the surroundings, and therefore sublimation is an endothermic process. And the opposite process of sublimation, that is taking a substance in the gas phase and transforming it directly into a solid without forming a liquid in between. Think about, say, gas phase water vapor molecules in the atmosphere touching very, very cold blades of grass in the morning, and then the frost that forms on the surface there. That process we call the process of deposition. So again, going from gas phase to solid phase, the opposite of sublimation is deposition. And because it's the opposite process, it must therefore also have the opposite change in energy, meaning therefore deposition is an exothermic process. So those are the familiar phase changes. Let's have a look at those now in the context of a phase diagram. All right, so now that we have talked about phase changes, let's go ahead and have a look at the relationship between these different phases as a function of two different variables. Those are temperature and pressure. As we introduced to you last year, phase changes do not only occur because of changes in temperature. A change in pressure can also affect the phase of matter. And so we're going to go ahead and draw here a quick phase diagram, we refer to these as, for a generic species here. And we're going to separate our diagram into three distinct regions of space. If you have a look over here, I'm going to just imagine kind of a point in this general region on the left-hand side of our diagram over here. Let's just choose a point up here, and you'll see that this point can exist at relatively high pressure, but at low temperature. So if we have high pressure, that would imply that the particles are being pushed close together, meaning this is essentially expected to be a relatively dense phase of matter. We've got a high proximity of those atoms to one another. And then a low temperature means there's not a lot of molecular motion in the system at this point, which sounds a lot like a description of a solid phase. So this region of space over here is the solid phase region of space. Have a look now, selecting another point over here. We'll select a point on the bottom right side of our graph now. This is a point at a high temperature and a low pressure. At low pressure, the particles are not going to be pushed close together. That is, there's going to be a lot of space between particles. And at high temperature, there's going to be a lot of molecular motion. This sounds very much like a gas phase system. So this region of space over here describes substances in the gas phase. And not surprisingly, in between, there's a third region of space where we're kind of intermediate both in terms of pressures and temperatures, and this is going to be occupied by our intermediate state of matter, that is the liquid phase. Now, considering here, if we take a point, say in this solid phase position here at this particular temperature and pressure, if I'm at these this current set of temperature and pressure conditions and I increase the temperature, you can see that it can cause the point to move across that boundary between the phases, which implies, therefore, the substance is going to undergo a phase change from solid phase to liquid phase. That is, it's going to melt. Now, important to note here, folks, is that melting occurs not as it's heating up, but melting occurs at the point where you cross the boundary. That is, it occurs at a specific point in your transition there. And so the point where you cross from the solid phase to liquid phase would be referred to as the melting point of that substance. Likewise, if I just reverse that whole process, I would go from a liquid phase species to a solid phase species, which implies the melting point and the freezing point of the substance are one and the same. They occur at the same temperature. What matters really is if it's an exothermic or an endothermic process, if you're absorbing energy from the surroundings or if you're adding energy to the surroundings. So that being said here, recognize that I could also change the state of matter, not by affecting the temperature, but I could also cross that boundary by moving up and down along the y-axis there by changing the pressure. This is a kind of familiar idea if you think about, let's say, a big canister of liquid propane fuel for, like, say, a backyard barbecue. If you've ever picked up one of those liquid propane tanks and moved it around, you can feel the liquid inside of there sloshing back and forth inside of the tank. But what comes out of the outlet when you turn on your burners is not a liquid, it's a gas. And the real idea there is that the state of matter, in addition to being temperature dependent, is also pressure dependent. At very, very high pressures inside the canister, we see the substance in liquid phase, but then as you open up the valve and let substance come out, the propane escapes, not as a liquid, but as a gas, because the atmospheric pressure outside is significantly lower than the pressure inside of the tank. So we could take something in the liquid phase and change it into a gas by decreasing the pressure, just the exact same way we could change the phase by increasing the temperature. All you have to do is cause it to transition across that phase boundary. So it's really a function of two variables. Those are pressure and temperature. Now, another key idea out of these phase diagrams that we need to understand is that the boiling point of a substance or a freezing point, or really any of those particular phase transition boundaries, can occur at various different temperatures depending upon what the pressure of the system is. So if you think for a moment here about normal atmospheric pressure of about 1 atmosphere, the temperature at which water boils at standard atmospheric pressure is a temperature of 100 degrees Celsius. But you'll notice here that on my phase diagram, if I decrease the pressure in the system, then the temperature required to cross that boundary becomes lower at lower pressures, which explains something we all know living here in Colorado, that is, at lower pressure, water boils at a lower temperature. Here in the area around Denver, it could boil around 93 or 94 degrees or so. So we recognize again that the boiling point really isn't one specific point. We call the normal boiling point the boiling point at 1 atmosphere, but really every point along this line that separates the liquid phase from the gas phase is a boiling point of the substance at a particular pressure. Likewise, the same logic applies to our melting points. We define the normal melting point as being the melting point, the temperature at which we see a phase change from solid to liquid at a pressure of 1 atmosphere. But again, if we change the pressure, we'd also expect to see a change in the melting points of the substances as well. All right, now a couple other ideas to cover on here. Have a look at the upper right-hand corner of our diagram, and you'll notice here that at a certain point I've labeled a little dot up in the upper right-hand corner there. Above this particular temperature, no matter how much pressure is applied to the system, the vapor cannot be liquefied. That is, the only phase available above that temperature is gas phase. And we call that particular point the critical point. And the temperature at which the critical point occurs is called the critical temperature. And the pressure at which that point exists is again called the critical pressure. So again, above that particular temperature, we cannot liquefy the species. It only exists in the gas phase. And one other important point to note on our diagram here, the point where all of those lines come together in the center, we refer to that as the triple point of our system. Now, to understand the triple point, let's go back and first examine again one of those points on the line between the solid and liquid phase. That is one of our melting points. If you are at this particular set of temperature and pressure conditions where we've diagrammed our point here, and you're not either adding or removing energy from the system, the big question then becomes, well, what's going on there? Is this substance melting? Is it freezing? Is it in solid phase? Is it in liquid phase? What's really going on when you're exactly at that particular temperature and pressure? And to understand that, let's have a look here at a diagram here. Here's a real quick drawing of let's say a system where I've got an ice cube in some liquid water, and let's assume that we're at exactly 1 atmosphere of pressure and a temperature of exactly 0 degrees Celsius, and we're not adding or removing energy from the system. Even though we're not adding or removing energy from the system, we still would expect changes to be taking place. That is, we have a dynamic system here, not a static system. There's still molecular motion because there's random thermal energy in the system, and because there's molecular motion, we can imagine that a couple of those solid phase particles on the surface of the ice might bump into one another, and in doing so, one of those particles might gain enough energy to overcome the intermolecular forces of attraction, holding it into that crystalline lattice and escape into the liquid phase. That is, that particular particle could melt. But at the same time, a liquid phase species could end up bouncing into the surface of this solid and lose a little bit of kinetic energy in that collision. The intermolecular forces of attraction could then pull it in and affix it to the surface of the solid. It could therefore freeze. So even though we're at a temperature of exactly 0 degrees Celsius, it's not that freezing and melting don't occur at that point. It's that both freezing and melting occur at the same rate. That is, the system has established a dynamic equilibrium. So another way of thinking about these phase boundaries is to think about them as a set of points where the two phases separated by that boundary exist in dynamic equilibria with one another, as long as we're not adding energy to the system or removing energy from the system in the form of either a change in temperature or pressure. Now, that being said, the triple point is a special case where all of those phases of matter, solid, liquid, and gas, would simultaneously therefore exist in dynamic equilibria with one another. And one important point to reinforce again the idea we brought up to last year, when we're talking about this dynamic equilibria, that doesn't mean that you've got equal amounts of the different phases in equilibria with one another, because equilibrium is not defined as a balance between amounts of substances. What really is going on there is that the rate of change in the two different directions across the phase boundary are equal to each other. So the rate of, for example, freezing would be balanced by the rate of melting. So just another way of looking at the phase boundaries there in terms of equilibrium rather than in terms of boiling points and melting points and freezing points like we've talked about before. So this hopefully should all have been review for you here, and let's go ahead and have a look on our next slide. So on this next slide here, we're going to be looking here at what we refer to as a heating curve, or conversely, we can also talk about a cooling curve. And in particular, I want to look at the relationship that exists between this heating curve and a phase diagram. So we can make a heating curve by looking at a system in which we're adding energy to a system at a constant rate and measuring the changes in temperature of the system as the time passes. So imagine for a moment here, we take a bunch of solid phase water that is ice, and we add energy to the system over time. And we just measure the temperature as the experiment goes on. I've drawn for you over here a phase diagram for water here. And one thing I want you to note about that phase diagram for water is the boundary between the solid and liquid line has a negative slope rather than a positive slope. And we can understand that by thinking about what would happen to our system if it experienced a change in pressure. Imagine that I take solid phase water, that is ice, and I increase the pressure on the system. If we increase that pressure, we would see that that would cause us to, at a certain point, cross the phase boundary between the solid phase and the liquid phase. That is, squeezing ice really, really hard, exerting the pressure on it, can cause it to melt. Now, that makes logical sense given one of the kind of weirdly anomalous properties of water that we're familiar with. That is, water is a substance which is more dense in the liquid phase than it is in the solid phase. The formation of the crystalline lattice with water molecules as it forms a molecular solid causes the formation of essentially little spaces between the water molecules due to the alignment of the hydrogen bonding within the solid there. And as such, we see it actually increase in volume as ice forms and those water molecules align themselves. So understanding then that if we're increasing the pressure, it would have a tendency to push the substance into a phase of matter in which it is most dense, it then seems logical we would expect to see an increase in pressure, cause it to liquefy because it is, again, more tightly packed together particles that we would see in the liquid phase than in the solid phase. Now that looks different from most phase diagrams because, again, most other substances are more dense in the solid phase, and as such, increases in pressure tend to push it into the more dense solid phase for most other substances. So let's imagine here for a moment here that we are at a pressure of 1 atmosphere pressure, and we're starting off at a very, very cold temperature, and we start our heating curve experiment. That is, we increase the temperature of the system by adding energy. So I'm going to go ahead and think about what happens here. As we add energy, we are going to move across our diagram here to the right. Temperature is going to be increasing. And note here as well, at the same time, we would expect to see an increase in the temperature of our substance recorded on our heating curve as well. And when we reach the normal melting point of ice, that is the temperature of 0 degrees Celsius, we'd expect to see a plateau occur as the process of melting begins. Now remember, even though we're still adding energy here to our system, that energy has to go somewhere, and energy is a conserved quantity, but what's going on in the system if we're adding energy and we don't see an increase in temperature? Now, to answer that question, remember, temperature really is a reflection of the average kinetic energy of those particles. And as such, generally increasing the temperature occurs when you add heat to the system. But remember, kinetic energy is not the only type of energy that exists. We also have potential energy, and in essence here, that is, in this point, energy stored within bonds or intermolecular forces here, attractive forces between water molecules within the crystalline lattice. To separate the lattice apart, we have to disrupt that hydrogen bonding which is taking place, and that is itself an endothermic process. So we can think about the event occurring here as melting occurs as essentially breaking up the solid lattice there, overcoming the attractive forces those hydrogen bonds exert between the water molecules. And once all of our substance has melted, then again, we would expect to see an increase in temperature occur again as we see now more thermal energy, that is more random molecular motion in our sample of liquid as it heats up. So from here to here, we're going to have heating a liquid. And again, we're going to get to a boundary there, which was now going to be occurring at a temperature of 100 degrees Celsius. That is our boiling point of water here. And just as before, we're going to see a plateau occur on our heating curve as the substance transitions from a liquid phase to a gas phase. Recognize again that we're still adding energy to the system, and now that energy is going to essentially separating the particles apart from one another, because in gas phase, there's a great deal more distance between particles than there is in the liquid phase. Because those particles are attracted to each other by IMFs, it then is therefore an endothermic process to separate them apart. So again, we're essentially increasing the potential energy of those particles by pulling them further apart from one another as we transition from liquid phase to gas phase. And once we're in the gas phase all the way, then we could expect to see again increases in the temperature of our vapor as we add more energy to the system. So we get this kind of staircase diagram for our system, for our heating curve of our system. Now, that being said, we can pick out a couple of pieces of information again in here. Remembering back to last year, as we look at our heating curve, the phases of matter are separated in terms of solid phase being the lower temperature state here, followed by liquid phase in the middle, and then gas phase up above. And the plateaus, again, are places where we see phase changes occurring. This first plateau would again be the point at which we are melting, and the second one, the point at which we are boiling. And I could then read off the side there of my diagram and find the respective melting points and boiling points of my substance by just seeing where those plateaus occur. Now, consider for a moment here, let's say I ran this experiment a second time, but this time at a significantly lower pressure. If I decrease the pressure and then go through the same events, have a look as we diagram again here. The first thing I'm going to see there is that I'm going to cross the boundary between our solid phase and liquid phase, if we are at a lower pressure, at a higher temperature. Now, it's not a whole lot higher for water here, because as it turns out, that line separating the liquid phase from the gas phase for water is very, very nearly vertical. It's exaggerated a little bit on your diagram, but it is meaningfully different there. So again, we would expect to see a phase boundary, which is going to be slightly to the right on the phase diagram, which implies at a slightly higher temperature was where my plateau is going to occur. And then if I continue across, now here's where the big change takes place. When I transition now from the liquid phase into the gas phase, we see now that at a lower pressure, that occurs at a significantly lower temperature. So my plateau for the phase boundary between liquid phase and gas phase would occur lower down, implying again that it requires less energy to separate apart those gas molecules from one another, those water molecules from one another to get them into the gas phase if we are at a lower pressure for water. So recognizing the relationship that exists here between the heating curve and the phase diagram, I can understand that I could generate a heating curve from a phase diagram for a substance without having to run the experiment if I knew what that phase diagram actually looked like. So that's kind of the key idea we want you to get here, is that we can go back and forth between heating curves and phase diagrams to pull the same sort of information out of both of those two separate diagrams. And for our last topic of conversation here for this particular lecture, we're going to look at the opposite event that we just described. This is now a cooling curve. Cooling curve is essentially the reverse experiment of a heating curve. Rather than adding energy to the system at a constant rate, we're instead going to be removing energy from the system at a constant rate. And in general, the same sort of information can be taken out of a cooling curve. Again, we would start off here at the left-hand side of our diagram in the gas phase, and then we would plateau when we saw a phase boundary as we move from gas phase to liquid phase. So at this point, we would expect to see condensation occurring. And then again, once all the substance has condensed to a liquid, the liquid would begin to cool. And as that liquid cools down, we would be cooling our liquid. But something kind of interesting happens here that doesn't really happen as much in heating curves, in particular for water. Have a look at the region of our diagram down here where we've got the little kind of dip. You'll notice there that that dip occurs down below the position where the freezing point of water is occurring there. That is below where that line plateaus. So in this little section of the graph right there, what we've got going on is what we refer to as a supercooled liquid. A supercooled liquid is essentially an unstable state in which the liquid exists below its freezing point. And the idea that we want to kind of get here is in order to actually go from liquid phase into the solid phase, we've got to arrange those particles of water by putting the positively charged hydrogen side of water molecules close to the negatively charged oxygen side of the adjacent water molecules. That is, we have to essentially form the crystalline lattice. And as the formation of that crystalline lattice is itself an exothermic process, we would expect then to see the temperature of the system slightly go up as the crystalline lattice forms. So what you're really seeing right there is a little dip followed by an increase in temperature as the lattice is actually forming between those water molecules. And this is actually kind of a very popular thing to see on YouTube these days. Some of you might have seen videos before of a supercooled liquid more or less instantaneously freezing if it gets jostled a little bit. So oftentimes what those videos look like is you'll have somebody take a bottle of water out of a freezer which has been in there for a while, chilled to a very, very cold temperature, and then as soon as they move it around there, then the supercooled liquid returns to its more stable position in which it solidifies, and we see a rapid solidification of the substance take place. And again, because the formation of the lattice is itself a exothermic process, we'd expect to then see an increase in temperature as that supercooled liquid heats up, forming its solid. And then beyond that point, then everything else looks normal as we would expect it to. We then would see after the solid has formed and we continue to remove energy from the system, the solid would decrease in temperature. So cooling curve, essentially the exact opposite of a heating curve. The one other thing to watch out for in those cooling curves is that possibility of forming those supercooled liquids for some substances. So that is it for our discussion of phases of matter here, and thanks for watching. We'll see you on our next lecture.